The story that leads to relativity began in the 19th century with the work of Maxwell, Faraday, and others on electricity and magnetism. They weren't originally trying to describe light, but when Maxwell discovered how to write equations that described electric and magnetic forces, an amazing thing happened, and those equations actually also predicted and described the propagation of light waves, and as it turned out later, also radio waves, TV waves, gamma rays, and so on, which are all different manifestations of the same basic phenomenon, the same basic kind of wave seen with different energies that came out of Maxwell's equations. And Maxwell's equations have the very funny property that they tell you that light waves will travel in any direction at the same speed that we call the speed of light, regardless of how the light waves are created. That's very funny because, for example, I might throw a ball and it has a certain speed, but if I'm standing on top of a railroad truck when I throw the ball, it'll come out with a bigger speed, the speed of the train plus the speed with which I can throw the ball. So the speed a ball has when I throw it isn't just a property of the ball, it also depends on my state of motion when I throw the ball. But Maxwell's equations say that light always has the same speed in any direction, regardless of how it was created. Now, it took decades before the significance of this sank in. For one thing, people didn't believe it. It was tested experimentally by Michelson and Morley, who found it was right. That wasn't, I don't think, what they thought they were doing when they did the experiment, but that was the answer they got. But even after the experiment, people were confused about what it meant, and physics was in a state of confusion in the late 19th and early 20th century. The time was right for a new theory, which was Einstein's relativity, but Einstein was the one who had the bold thinking to put it together. Einstein's point of view was to accept that the equations of electricity and magnetism were correct, and that our traditional intuition, which physicists expressed in the form of Newton's laws of motion, was what had to change. So he developed a new theory, or at least a new way of looking at existing theories. He modified Newton's laws, but he kept, in pure form, Maxwell's equations of electricity and magnetism, and that was how he created special relativity. Special relativity, I think, was a little bit like calculus. Calculus had been invented centuries earlier by Newton and Leibniz, and it changed the world when they invented calculus. It was far more powerful than what was there before. However, the time was ripe for it, and their contemporaries were inventing bits and pieces, although they didn't see the whole picture. It was a little bit like that when Einstein invented special relativity, which is what I've described, where he modified Newton's laws to deal with the reality of the properties of light. But 10 years later, Einstein did something far more marvelous, and for this the world really wasn't ready. If it hadn't been for Einstein's vision, it would have been a long time before this would have been done. Einstein recognized and understood far more sharply than anyone else at the time that not only were Newton's laws of motion inconsistent with Maxwell's theory of light, but Newton's laws of gravity were inconsistent with special relativity. And again, he recognized that it was Newton's theory that had to change. So he developed a new conception of gravity that, in a sense, was made by imitating Maxwell's laws of light. But it turned out to be a much more difficult and much deeper theory. In technical language, it's a nonlinear theory. The geometry that's involved that he needed to use was much more sophisticated than any mathematics that physicists had dealt with before. He had to use and develop the theory of curved space-time, and his basic concept was that when a planet goes around the sun, it's not because it's attracted to the sun, as Newton would have said. Rather, the sun has created curvature in space-time, and the planet is trying to find the closest thing to a straight line in a curved space-time. Just like Einstein's theories were developed to resolve contradictions between previously existing theories. The same was true for quantum theory. In fact, it happened, or it got started, in the same period that Einstein was developing relativity theory, and he himself was one of the protagonists. With quantum theory, the trouble started when the electron was discovered, just near the beginning of the 20th century. And the problem with the electron, it's an electrically charged particle, and as far as one could see, it was just a point particle, but at any rate, it was much smaller than anything known. And there was also the atomic nucleus discovered by Rutherford in his famous scattering experiments. And then there's a problem, which is that the electron attracted to the atomic nucleus by electrical forces should be emitting electromagnetic radiation, otherwise known as light waves, according to Maxwell's theory of electromagnetism. And when physicists calculated how long it would take an electron to spiral into an atomic nucleus, and therefore for the atom to collapse, by emitting light waves, they got a ridiculously small time, much less than a millionth of a second. So clearly something was wrong, and a new kind of theory was needed. So Bohr took a famous step in 1913 with the Bohr atom, where he just guessed some rules whereby classical physics was incomplete, and the electron just wasn't allowed to tumble all the way into the nucleus. But these rules didn't come with a coherent set of equations. You couldn't really calculate the energy states of an atom. Bohr proposed that there were energy states, and he had some sort of arbitrary rules for what they would be in a few cases. But the 1910s were a period of tremendous experimental progress, and lots of discoveries were made that gave clues that a new kind of theory was needed. And eventually it was put in its contemporary form in the 1920s, when physicists got the brilliant idea that an electron, although it looks like a particle in most respects, can also be treated as a wave. And somehow the wave-like properties of the electron cause it to be spread out and make it impossible for the electron to spiral all the way into the atomic nucleus. There was an amazing constellation of intellectual history and the development of technology that made decisive experiments testing this possible at almost the same time that the theoretical idea emerged. The decisive experiments were made by shining a beam of electrons on a crystal of atoms and looking at the directions with which the electrons emerged. So if you treat the electron as a classical point particle, it could come out in any direction. But waves have special behavior, which in everyday life you see, for example, if you see a rainbow in the sky, where scattered waves come out at preferred directions. A rainbow is created because the preferred direction depends on the color of the light. For an electron, the color corresponds to the electron's energy. When it scatters from a crystal, it'll come off with preferred directions depending on its energy. And this was actually observed experimentally in around 1925 by Davison and Germer. If you're curious where they got the electron beams that they scattered from their crystal, well, old-fashioned televisions, not the modern plasma screens, but old-fashioned televisions were based on creating electron beams that make light spots when they meet the screen that you see. So technology creating electron beams has been important in the last century. And one of its applications was to test this basic idea of quantum theory.
Da sempre gli scienziati, nel tentativo di giungere a una visione completa e risolutiva delle leggi naturali che governano l'universo, cercano di formulare teorie sempre nuove e più ampie. Alla fine del XVII secolo, Isaac Newton compie un passo fondamentale nella comprensione dei diversi aspetti della natura, unificando la fisica terrestre e quella celeste. La visione di Newton rimane invariata fino a quando Einstein solleva nuove questioni. Nella fisica newtoniana, la forza gravitazionale si trasmette istantaneamente attraverso lo spazio da un corpo all'altro. Questo è incompatibile con la relatività ristretta che afferma che niente può viaggiare a una velocità superiore a quella della luce. Einstein, superando la visione di Newton, arriva a proporre una nuova legge di gravitazione, che espone con la teoria della relatività generale. La teoria della relatività diviene uno dei pilastri fondamentali della fisica contemporanea. L'altro è costituito dalla meccanica quantistica, che ha origine con la teoria dei quanti formulata nel 1900 da Max Planck. Mentre la relatività generale fornisce un quadro di riferimento per la comprensione delle leggi universali a livello macroscopico, la meccanica quantistica spiega le proprietà dell'universo a livello atomico e subatomico e mostra che in alcuni casi i concetti che stanno alla base della fisica einsteiniana non hanno valore se applicati a scale molto piccole. Per questo motivo, le due teorie appaiono in contraddizione e anche se entrambe sono state confermate sperimentalmente, sembrano tra loro incompatibili. Questo dilemma costituisce il nodo centrale della fisica contemporanea, superabile solo con una nuova teoria unificata, in grado di descrivere tutte le forze della natura all'interno di un quadro coerente. Molti studiosi vedono oggi nell'innovativa e affascinante teoria delle stringhe una possibile risposta a questa esigenza.
By now, physicists had learned that when they've got two different theories that describe different things, it's important to try to make them work together and see what happens. Einstein had invented special relativity because the theory of light didn't agree well with Newton's laws, and he had invented general relativity because of a similar problem involving Newton's theory of gravity. And then quantum mechanics had been invented because the existence of the electron seemed to contradict the wave theory of light. So by the time quantum mechanics was invented, this idea that you had to take seriously contradictions between existing theories was well established. And one of the first things that physicists started to consider was how the new theory of quantum mechanics could be combined with Einstein's work. So the first part of that was to unify quantum mechanics with Einstein's theory of special relativity. Remember, special relativity is Einstein's theory where he modified Newton's laws of motion to agree with the fact that light always travels in the same velocity regardless of how it's created. It turned out that in combining quantum mechanics with special relativity can be done, but it led to a marvelous and very surprising new world. A lot of the original work was done by Paul Dirac, the famous British physicist, and he invented a new equation for the electron, which was a relativistic equation. Unlike the earlier, the first form of the quantum equation for the electron, Dirac invented a relativistic equation, but had a very funny property that was tied to deep facts about relativity. It predicted the existence of antimatter. And again, there was a nice coincidence that technology advanced in such a way that the existence of antimatter could be tested experimentally pretty soon after Dirac had predicted it. It was originally discovered in cosmic rays. Cosmic rays are rays that come to us from space. Even today, 80 years later, how they're created isn't completely understood. Many low-energy cosmic rays, for example, are created by the sun, but at very high energies, we still don't know where cosmic rays come from. Anyway, though, scientists taking photographic plates used to detect cosmic rays up to mountaintops, they discovered that not only were there ordinary electrons, but also there were antimatter electrons or positrons in the cosmic rays. The positrons are just like electrons in terms of their mass, but they have the opposite sign of the electric charge. And they have the amazing property that when an electron meets a positron, they annihilate into pure radiation, into electromagnetic waves. The point of quantum field theory, in a sense, is that it taught us that matter, antimatter, and radiation are all different ways of looking at the same thing. Matter and antimatter can combine into radiation. Radiation can combine into matter and antimatter. And it's all described by a system of relativistic equations that's far more unified than anything that anyone had had before. There's something that people who aren't physicists usually tend to not understand about modern physics. Because of Einstein's great fame and the fact that his work was on a much deeper plane than anything that had come before, people tend to assume that the most difficult theory that physicists grapple with is Einstein's work. But actually, it's not true. Since quantum theory, and especially since the work of Dirac on relativistic quantum theory, the most difficult theory in modern physics by far is quantum field theory. It's an extremely difficult subject. Well, it was the work of most of the 20th century to understand it better. We're still understanding it better, but you could say that the modern understanding took half a century from Dirac until what's called asymptotic freedom, a pivotal discovery made in the 70s that made it possible to understand the atomic nucleus. A whole chain of Nobel Prizes went into understanding quantum field theory, which was the theory by which physicists combined quantum mechanics with special relativity. Not with Einstein's general relativity, only with his simpler theory of special relativity. The point we've reached in the story so far is the success physicists had in combining quantum mechanics with Einstein's first theory, special relativity, that describes how light has the same velocity regardless of how it's created. Of course, people wanted to go on and combine quantum mechanics with Einstein's deeper theory of general relativity, his theory of gravity. But as first became clear in the 1930s, that actually didn't work, at least not in any straightforward way. If one tries to apply the quantum principles to general relativity, Einstein's theory of gravity, one runs into a web of contradictions. One finds that the nonlinear mathematics that Einstein needed for general relativity simply doesn't work well in the context of quantum theory. In a way, it has to do with the old problem of the electron spiraling into the atomic nucleus. Physicists grappled with that problem in different ways throughout the 20th century. So, quantum theory without relativity solved it. Then when they included special relativity, the problem actually got worse again. And it took another 20 years, and it actually wasn't completed until about 1950, leading to the Nobel Prize of Feynman, Schwinger, and Tominaga, when the problem of the electron spiraling into the nucleus was solved in special relativistic quantum theory. But in general relativistic quantum theory, where you worry about the electron spiraling into the atomic nucleus because of gravitational forces, all this still didn't work. And as far as we understand today, and of course we don't know everything, but our best understanding today is that general relativity in ordinary four-dimensional spacetime, and remember it's four-dimensional because Einstein taught us to count the time as well as the three obvious space dimensions. Our best understanding today is that general relativity in quantum theory just doesn't work. Something needs to be modified.
I fisici di tutto il mondo tentano da decenni di elaborare una teoria in grado di descrivere l'universo in tutte le sue dimensioni, unificando i risultati della relatività generale e della meccanica quantistica. A partire dagli anni 50, l'attenzione degli scienziati si concentra sullo zoo di particelle elementari messo in luce dagli esperimenti condotti al CERN di Ginevra. Ha così inizio la ricerca di principi in grado di descrivere le leggi fondamentali della natura a partire dai suoi costituenti elementari. Il ricercatore Gabriele Veneziano compie il primo passo nel 1968, quando trova una formula in grado di descrivere le proprietà di buona parte delle particelle rilevate. A partire dalle sue ricerche, i fisici Yoichiro Nambu, Holger Nielsen e Leonard Susskind propongono per queste particelle il modello di piccole stringhe. Ne emerge una nuova teoria che prende proprio il nome di teoria delle stringhe e che appare a molti la candidata più promettente per svolgere la funzione di teoria unificante. Alla sua base vi è l'ipotesi che le particelle non siano puntiformi, ma siano costituite da un minuscolo filamento, detto stringa, che vibra e oscilla, determinando, a seconda del modo in cui avviene la vibrazione, le caratteristiche fondamentali di tutte le particelle, la massa e la carica. Ma in che modo la sostituzione di una particella puntiforme con una stringa può risolvere il problema dell'unificazione tra la meccanica quantistica e la relatività generale? Nel 1974 i fisici John Schwarz e Joel Scherk avanzano l'ipotesi che uno dei modi in cui una stringa oscilla corrisponda perfettamente alle proprietà del gravitone, la particella mediatrice della forza gravitazionale. Questo confermerebbe che la teoria delle stringhe è in grado di collegare la gravità descritta dalla relatività generale con la struttura delle particelle descritta dalla meccanica quantistica. La natura di questa nuova teoria è però talmente rivoluzionaria e ambiziosa che finora non ha condotto a risultati sperimentali. Sarà necessario molto lavoro prima di poterla considerare compiuta, ma nel frattempo si candida a diventare un'unica e onnicomprensiva teoria del tutto.
So in the 40s, 50s, and 60s, of course, physicists wanted to reconcile quantum mechanics with Einstein's general relativity, but there weren't any ideas worth remembering, really. But in the meantime, other things were happening, because the particle accelerators were invented and became important starting in the 1950s, and a wealth of new things were discovered. There were new particles and new forces and new phenomena, like what we call parity violation, a fundamental asymmetry of nature between left and right, where the laws of nature just don't look the same if you look in a mirror. A lot of very strange things were discovered, and the focus of trying to understand the fundamental laws of nature shifted in the 50s and 60s away from questions like trying to understand gravity and more toward trying to understand the elementary particles. But the continuation of our story involves an idea that developed in the 1960s, which from a modern point of view was possibly only half correct the way it was originally interpreted, but it turned out to be the seed of many wonderful later discoveries. A lot of it had to do with the work of Italian physicists, actually, including Regge, Veneziano, Fubini, Virasoro, and too many for me to mention in full detail here. But there was the experimental discovery that there were more and more strongly interacting particles as we increased the energy at the particle accelerators. And then there was an idea that sprang from work of Regge that these particles should be put in what are called Regge trajectories, that many different particles, in some sense, are different forms of the same thing. And then there were ideas that people had about writing some kind of a fundamental equation that would describe all this mess. And the properties that people wanted looked impossible. Some very distinguished physicists were very close to writing papers saying it was impossible, when then Gabriele Veneziano found a way to actually do it. That was his famous paper, written in 1968, where he gave a formula with wonderful properties that qualitatively looked like it was a lot like the world of the strongly interacting particles. Well, it only described half of the strongly interacting particles, and we'll discuss the other half later on. But for half of the particles, perhaps not the ones you've most heard about, most people will know about protons and neutrons. Veneziano's original work had more to do with particles you may know about less, like pions and rho mesons. But in my line of work, if you're interested in the fundamental laws of nature, the pions and the rho mesons are as important as the protons and neutrons, and Veneziano had an amazing formula that describes some of their properties. And as physicists worked harder on understanding what the Veneziano formula meant, they discovered more and more amazing things. This unfolded over a period of perhaps 5 years, from about 1968 to 1973, when there was very intensive work on this subject. It culminated in the understanding that although Veneziano had no inkling of this when he first wrote down his formula, the Veneziano formula is best understood as an equation describing the behavior of little strings, little loops of string in space. So the idea going back to Reggie had been that different particles were different forms of something. Well, in the Veneziano model, what they're different forms of is different states of vibration of a string. Just like a piano string can vibrate in different shapes or harmonics, leading to a fundamental tone and its higher overtones, which are responsible for the beauty of music. In the context of the Veneziano model, the pion, the rho meson, the omega, the phi, and various other things that perhaps will be less familiar, are different states of vibration of one basic string. When physicists started to study string theory, originally in the period from about 1968 to 74, they discovered a lot of amazing and wonderful things. The theory was amazingly rich. It had properties that are quite surprising if one is accustomed to the standard quantum theories. And in some ways, its properties are better. I'd like to illustrate the differences with a little picture. And you should understand this picture as a picture that describes the motion of particles in space and time. Time is going vertically, and space runs horizontally. So, for example, this diagonal line and this one describe the motion of particles that come in from the past. Then they go out to the future over here. And in between, there are some processes at space-time events labeled P, Q, R, and S, where the particles branch or rejoin. Either one breaks into two or two recombine into one. And all the complications of standard quantum theory come from the rules for what kind of branching and rejoining is allowed, and also from the fact that you have to, according to Feynman, allow all possibilities for what P, Q, R, and S were, when those moments were in space-time. And when they happen to coincide, you run into the infinities that correspond to the electron spiraling into the atomic nucleus. Now here's the equivalent picture in string theory. First of all, a point particle has been replaced by a little loop of string. So a line representing the path of a point particle in space has been replaced by a little tube. And unlike lines which branch or rejoin at definite moments where something happens, the tubes can join in a completely smooth fashion. So while this is a traditional Feynman diagram, this is the equivalent in string theory. Since there are no distinguished moments, P, Q, R, and S, the complications of the many possible theories that come from describing what's allowed to happen at those moments completely disappear. And instead, in the case of the string, once you know what the string is, you also know how it interacts. It interacts by just these smooth processes. In the mathematical jargon, this is a smooth two-manifold, but this one manifold has singularities at definite events where something happens. The infinities go away because they're tied to these definite events, and also the vast number of choices of conceivable quantum theories disappears because of the same thing. So when, for example, Weinberg, Lascaux, and Slom invented later on the standard model of particle physics, they in effect gave rules for what happens at P, Q, R, and S. Those rules are rather detailed and complicated. They work experimentally, but it's a long story, and it has to do with selecting one theory rather than another. Whereas for the string theory, when you know what the string is, you automatically know how it interacts.
Nella formulazione originale di Gabriele Veneziano, la teoria delle stringhe è in grado di descrivere le proprietà di circa metà delle particelle legate da interazioni forti. Per giungere a incorporare l'altra metà è però necessario compiere un passo ulteriore. Nei primi anni 70, grazie ai lavori di Pierre Ramond, John Schwarz e André Neveu, si fa strada una nuova versione della teoria, che prende il nome di teoria delle stringhe supersimmetrica o teoria delle superstringhe. Da questa nuova formulazione emerge un sorprendente fenomeno, la supersimmetria. Alcune particelle sembrano infatti presentarsi in coppia, vale a dire che ad ogni particella conosciuta ne corrisponde un'altra di aspetto sconosciuto, ma di comportamento simile. Se risulterà corretta, la supersimmetria diventerà parte fondamentale della nostra comprensione della natura, perché grazie ad essa sarà possibile determinare indirettamente le caratteristiche di alcune particelle, a partire dallo studio delle proprietà fisiche dei loro partner. Le particelle supersimmetriche non sono mai state rilevate sperimentalmente, ma i fisici delle stringhe sperano che gli esperimenti condotti nei potenti acceleratori del CERN possano un giorno dimostrarne l'esistenza.
Because of what I've just explained, string theories are much scarcer than conventional quantum theories. And if you have something that works, it's very hard to change it so that it still works. And it's very hard for anything to work at all. String theory just barely hangs together consistently, and a lot of surprising discoveries were made in the process of making sure that it did hold together. So in the early period, from 68 to 74, there were perhaps 3 crucial discoveries that came out of trying to make the theory work and hold it together. First of all, Veneziano had only described half of the particles in the world of strong interactions, and not the half that most viewers of this CD will probably be familiar with. Not the proton and neutron, only the ones familiar in my line of work, like the pion and the rho meson. So, seeking to modify the theory to include all these strongly interacting particles, including the proton and neutron, it was difficult, first of all, and the physicists who did it, including Ramond and Neveu and Schwarz, had to invent a new structure that eventually developed into what we now call supersymmetry. Supersymmetry is a new structure in the world of elementary particles. It predicts the existence of new particles in nature that we hope to eventually discover in accelerators. We'll get back to that in more detail later on. And its root had to do with trying to modify string theory to describe all the particles. Then there were 2 other discoveries made in this early period that, in a sense, caused the theory to go into eclipse, because most physicists at the time thought that these discoveries meant that something was wrong. First, it was found that string theory, for its consistency, required extra dimensions of space-time. And secondly, it was discovered that for its consistency, string theory needed particles of 0 mass, like the electromagnetic wave, or like gravitational waves in Einstein's theory, but unlike the strongly interacting particles, which they were trying to describe with string theory. Just as these discoveries were being made in string theory, something else happened, which caused string theory to go into eclipse for a while. And that was that there was a fundamental new idea about building the strongly interacting particles out of quarks, and what kind of new trick in standard quantum theory would make that possible. That new trick was called asymptotic freedom, and it eventually led to the Nobel Prize for Gross, Wilczek, and Pulitzer. So, for 2 reasons, string theory went into eclipse. First, the progress with more standard theories made string theory seem unnecessary, at least as a theory of strong interactions. And second, the discoveries that had been made, like large extra dimensions and unwanted massless particles, made it seem that string theory was wrong as a discussion or approach to strong interactions. So the number of physicists working on string theory went down probably from hundreds to practically zero. But the theory did not quite go into eclipse because it had a small number of fans. This is actually the period when I was in graduate school, and I wasn't yet conversant enough of things to quite understand what was going on. But the ones who kept it from going completely into eclipse were a small group of fans, such as Joel Scherk and John Schwartz, Michael Green, Lars Brink, and just a handful of others. And they must have been partly motivated by the fact that string theory had proved to be such an incredibly rich thing that hung together so miraculously that they couldn't believe it had just been a dead end. But there was a more specific thing, which is that, the massless particles had come out and nobody wanted them, and dozens of papers had been written by people who didn't want them trying to get rid of them, and it hadn't worked. So finally, people working on string theory had accepted that it really did predict unwanted massless particles. But Olive, Scherk, Schwartz, and a handful of people had the following brilliant idea: that a quantum theory with these extra massless particles wasn't wanted for the strong interactions, but there is something else in nature, which is an even bigger problem, where it is needed for. And that's the problem of combining Einstein's theory with quantum mechanics, Einstein's theory of gravity. As I told you before, if physicists grappled through the 20th century with the problem of the electron spiraling into the nucleus, and several versions of the problem were solved, but the gravitational version was not and has not been solved in standard quantum theory. During this period when string theory went into eclipse, a small number of physicists had the vision that maybe it should be reinterpreted as an approach to this other problem of reconciling gravitational theory with quantum mechanics. When they started working on that, it actually had a lot of success. Very, very beautiful work was done by Green and Schwartz and Brink, among others, but not very many others, in the late 70s and early 80s. It actually is the period that got me interested in this. By the summer of 1982, I had certainly noticed the work of Green and Schwartz. I remember studying my summer vacation in 1982, studying a review article that John Schwartz had written describing some of this work. They had shown rather convincingly, in my judgment, and it's a judgment that I would not change 28 years later, that even though they didn't understand it well, there was there a consistent theory that overcomes the traditional problems of making a quantum relativistic theory of gravity. And in doing that, supersymmetry was a very important ingredient. Supersymmetry had been invented before just to include protons and neutrons in Veneziano's theory. And then Scherk and Olive, with the Italian physicist Iozzi, had shown around 1976 that actually string theory generates supersymmetry in space and time, leading potentially to a new angle on the elementary particles. So during this period, string theory was revived with a new application in mind. It didn't yet attract wide interest of physicists, but it was there as a remarkable idea about a very big unsolved problem of reconciling gravitational theory with quantum theory. So by the early 80s, it was pretty clear that there was something big that Green and Schwartz and their friends were doing. It didn't yet have the attention of most physicists, but speaking personally in that period, I just had the feeling that something was going to happen. And there was a question that really bothered me about their work, actually, which is that one of the big discoveries in elementary particle physics had been what we call parity violation. If you look at yourself in a mirror, you look different, but you look like a possible person as far as you can see. In other words, in everyday life, the mirror image of something is another thing that might have existed in the world, even though it doesn't. As far as we know in everyday life, it looks like the laws of nature are completely symmetrical between left and right. But physicists had discovered, first in the 50s, and then it was incorporated in the standard model of elementary particle physics in the 60s and 70s. Nature is actually asymmetrical between left and right, and specifically the weak interactions that describe atomic radioactivity have a handedness built in. The neutrino that comes out always spins one way, and the antineutrino always spins backwards. And that's a fundamental asymmetry between left and right. And it looked to me in this period that string theory, at least in the forms that were known, could break the symmetry between left and right, but not in the way that nature does. It's not that string theory was left-right symmetric, but when you tried to describe the weak interactions in string theory, they were left-right symmetric. Well, Green and Schwartz made a fundamental breakthrough in 1984, their anomaly cancellation mechanism, which really put string theory on the map for most physicists. They solved this problem of parity violation in the weak interactions, and a whole lot of other things came out besides. So suddenly it became possible to use string theory to make models that not only described gravity and quantum mechanics, but described the elementary particles in a way that got correct most of the highlights, although not all the microscopic fine details. It was a very exciting period in the mid-'80s when there were a lot of things that could be done, and the picture developed very intensively.
La teoria delle stringhe è un episodio senza precedenti nella storia della fisica moderna. Dopo decine di anni di ricerche, condotte da migliaia di scienziati, le sue predizioni non hanno ancora ricevuto una conferma sperimentale. L'esistenza stessa delle stringhe, gli elementi che stanno alla base della teoria, non è mai stata accertata, poiché le loro minuscole dimensioni non sono rilevabili dagli attuali strumenti. Per questo motivo è aperto da anni un dibattito sulla sua validità scientifica. Uno degli elementi che suscitano perplessità è che questa teoria sia in grado di descrivere l'universo nella sua integrità a partire dallo studio delle particelle elementari e delle loro interazioni. Alcuni studiosi sostengono infatti che, al crescere della complessità del sistema di riferimento, debbano necessariamente entrare in gioco altre leggi fisiche. I sostenitori delle stringhe ammettono che l'universo è troppo complesso per far sì che una sola teoria possa fornire una descrizione globale di tutti i suoi aspetti, ma spiegano che la scoperta di una teoria del tutto segnerebbe solo il punto di inizio. Sarebbe un solido fondamento sul quale costruire una profonda comprensione del mondo. Un'altra caratteristica che attira aspre critiche è la sua eccessiva ricchezza. Si dice che esistano tante teorie delle stringhe quanti sono i teorici. Negli anni '80 si sono sviluppate 5 varianti di quella che dovrebbe essere la teoria del tutto. I fisici si sono accorti infatti che la supersimmetria poteva essere inclusa nella teoria delle stringhe in 5 modi diversi, cosa che ha creato non poco imbarazzo all'interno della comunità scientifica. Ricerche più recenti affermano però che le 5 teorie delle superstringhe altro non sono che diversi modi di descrivere una stessa teoria onnicomprensiva, secondo uno schema unificante proposto da Edward Witten con la sua cosiddetta teoria M.
In the understanding that emerged after the work of Green and Schwartz, it seemed that there were 5 fundamental possible string theories. If you wonder why there are 5, well, they differ by basic properties of the string. For example, in 4 of the theories, a string is a little closed loop, a vibrating closed loop of string. In 1 of them, the string is allowed to have endpoints. In 2 of the theories, the string conducts electric current, and in the other 3 theories, the string is an electrical insulator. Conceptually, having only 5 string theories was a big advance over standard quantum theory, where there are infinitely many possible theories, and traditionally, physicists are supposed to find the right theory based on experimental clues. For example, that's how the standard model of elementary particle physics was invented in the 60s and 70s, where the right building blocks, quarks, leptons, photons, and so on, and the right fundamental branching rules were discovered based on experimental clues. There were infinitely many possible theories, and you're supposed to find the right one. The consistency of string theory is much tighter. Instead of infinitely many possible theories, there were only 5, and one of them, the E8 times E8 heterotic string, looked like a particularly good candidate for describing the real world. Having only 5 theories instead of infinitely many is a big advance, but it leaves you slightly dissatisfied, because why not go all the way? We only live in one universe, not 5 of them. And if there are 5 theories, one of which describes us, you're left with the question, well, who lives in the other 4 worlds? Unlike a lot of big questions in the subject, the question of why there are 5 string theories and not just one actually has been answered. In the period around 1994 and 1995, and this is something I played a little bit of a role in, it was found out that the 5 string theories are actually different limiting cases of one bigger theory. There's one bigger theory, which we don't understand very well. We've been grappling with it in different ways ever since Veneziano's work of 1968. But there's one bigger theory that has the 5 traditionally known theories as limiting cases, and it also has got another limiting case that involves something called 11-dimensional supergravity. If you want to know what I mean by a limiting case, you should, roughly speaking, imagine a world with 2 variables, both of which will be unfamiliar to most of you. One of them is the quantum nature of the universe, measured by Planck's constant, h bar, and the other is the stringy nature of the universe, measured by what's called alpha prime, that was a fundamental constant in the Veneziano amplitude. So in a 2-dimensional space that measures stringiness and quantumness, the 5 string theories are different limiting cases. And when that picture was developed, at the same time, we acquired a much more comprehensive understanding of the mathematics involved. And we understand that there are many more possibilities and more limiting situations to explore, far beyond what we imagined in the past. When string theory had gone into eclipse in the mid-70s, well, one reason was that it didn't seem needed, and then there were the 2 things people didn't like, the extra massless particles and the extra dimensions. Well, the fact that it didn't seem needed was dealt with by finding a new mission for the theory, which was to describe not the strongly interacting world, but everything, including Einstein's general relativity, the quantum theory of gravity, and all the elementary particles. And for that, the massless particles that had seemed troublesome were needed. They were the quantum unit of Einstein's gravity. But finally, the extra dimensions were also needed to unify all of the elementary particles with everything else, to have room to describe the richness of the elementary particles as different states of one vibrating string. It turns out that if the string just vibrates in the known dimensions, that's not quite enough. You need the extra vibrational freedom of the string to vibrate in hidden dimensions, to give it the richness to describe not just gravity and electromagnetism, but also different kinds of quarks and leptons, neutrinos, W bosons, and all of the surprising things that have been discovered in particle accelerators over the decades. So ultimately, extra dimensions were understood as a blessing in disguise. The period following the unification of the string theories in the mid-90s was one when the perspectives of string theorists about what the topic meant are much broader. And as a result, a lot of things have been discovered that would have been hard to imagine beforehand. Certainly, though, the most fundamental of these is the discovery by my colleague Juan Maldacena here at the Institute for Advanced Studies of a fundamental duality, as we call it, between quantum gravity, which remember is the hardest thing in physics to try to understand, and a conventional theory without gravity. The picture is a little bit like a hologram. An ordinary photograph captures a picture of three-dimensional reality in 2 dimensions, but it loses some information. You can't see the perspective of the three-dimensional scene properly from a 2-dimensional projection. A hologram is a more sophisticated way to capture a three-dimensional reality in 2 dimensions. And from a hologram, you can reconstruct the spatial relations in 3 dimensions. But the cost is that the information is stored in the 2-dimensional sheet in a way that isn't intuitively obvious at a glance. You need to know how to read the hologram. Well, Maldacena discovered something similar for gravity, that a world like the one we live in, that has gravitational forces in it as well as quantum mechanics, and there are 3 space dimensions plus time, is actually equivalent to a different description with only 2 spatial dimensions plus time, which captures a holographic image of our reality in a theory that's a more conventional type of quantum theory without gravity. So there are 2 descriptions. There's the one that we experience in everyday life, 3 space dimensions and gravitational forces that hold us down to Earth and keep the Earth moving around the sun. There's a holographic description, 1 dimension less, no gravity, standard quantum theory of the type that is difficult. It's what physicists have grappled with since 1930.
Durante il congresso Strings 1995, Edward Witten stupisce i presenti annunciando di aver trovato una soluzione al problema di sovrabbondanza che affliggeva la teoria delle stringhe. Presenta infatti uno schema onnicomprensivo nel quale confluiscono e si fondono le diverse teorie emerse dagli studi degli anni '80, che fino ad allora erano considerate del tutto disgiunte una dall'altra. Questo schema unitario viene denominato teoria M. Quale sia il preciso significato della lettera M non è noto. Lo stesso Witten dice che potrebbe essere membrana, matrice o madre, nel senso di madre di tutte le teorie. Sebbene siano ancora molti gli aspetti oscuri, 2 caratteristiche fondamentali della teoria sono già state identificate. La prima è che le stringhe descritte possono vibrare in 11 dimensioni spazio-temporali e la seconda è che in essa è prevista l'esistenza di altri minuscoli elementi, come membrane bidimensionali o masserelle tridimensionali oscillanti. La natura più completa della teoria rimane comunque in gran parte sconosciuta, tanto che qualcuno sostiene che il significato della lettera M sia proprio mistero. Nonostante le difficoltà, i teorici delle stringhe sono convinti che essa possa costituire il passo fondamentale nella ricerca della teoria del tutto, quella capace di riunire in una descrizione coerente l'insieme dei fenomeni naturali. Come ha osservato lo stesso Witten, capire cosa sia realmente la teoria M modificherebbe la nostra comprensione della natura in maniera non meno radicale di quanto abbiano fatto le grandi rivoluzioni scientifiche del passato. Questa potrebbe essere la nuova frontiera della fisica del XXI secolo.
My personal view is that string theory probably is on the right track toward a much better understanding of nature. We don't understand the theory very well, but there are too many things about it that circumstantially look right for me to believe that it isn't on the right track. There's the fact that standard quantum theory doesn't work with gravity, while string theory forces us to include gravity. There's the fact that the qualitative aspects of the elementary particles come out so neatly. There's the fact that the consistency of the theory hangs together so miraculously, overcoming so many potential pitfalls, any of which could have led to a hopeless contradiction, which instead were overcome always learning that the theory had a tighter structure than was understood before. Even my own work on unifying the string theories had to do with an attempt to prove that they were inconsistent, that one of them was inconsistent. And that proof actually instead led to a better insight about how the different theories were different sides of the same coin. So my personal view is that string theory knows a lot of things that humans don't. We'll be grappling with it for a long time. I think it knows a lot of deep secrets about our universe. I can't promise how far we'll get in understanding them. All we can do is to do the best we can. The biggest experimental discovery of our times, of modern times practically, certainly of the last 20 years, has been the discovery that the expansion of the universe is accelerating. Ever since the expansion of the universe was discovered in the early 20th centuries, where we found that the galaxies are flying apart since the Big Bang, it was generally assumed that because of gravitational forces that tend to pull the galaxies together, this acceleration would be slowing down. But finally, by around 1997, techniques developed enough so that the rate at which the expansion was slowing down could be measured, and it was discovered that the expansion of the universe is actually speeding up. Although we don't know for sure that this interpretation is right, the simplest interpretation is that the energy of the vacuum is not quite zero, but is just slightly positive, corresponding to an energy density that's roughly the rest mass of one atom in every cubic meter of space. Einstein had envisaged this idea of a non-zero vacuum energy modifying his theory, but he rejected it, and in his day there was no experimental evidence in favor of it. In modern times, though, it seems that actually the vacuum, ordinary empty space, seemingly with no matter at all, still has this tiny energy density equivalent to one atom per cubic meter, which in general relativity causes the acceleration of the universe to accelerate. It has the consequence, if it goes on this way, that galaxies we can see today will be out of sight in tens of billions of years. And it's made many physicists suspect that there are other things that have gone out of our sight even earlier because of essentially the same phenomenon. And thinking further, it's caused physicists to suspect that some of the regions out of sight might be quite different from the regions that we can see currently. String theory seems to, with our best understanding of today, allow for this possibility that in a vast, vast universe, there are different regions where the quantum state has adopted a different configuration, leading to different details of the elementary particles, and to the possibility that aspects of what we observe are not uniquely determined by the way the laws of nature are, but partly by which solution of the equations of nature happens to be relevant in the region of the universe that we're able to see currently. I don't know for sure whether this thinking is correct. I'm not even sure I like it. As a physicist, I would like to be able to calculate everything, including the mass of the electron and the lifetime of the muon, and all kinds of things that listeners or viewers perhaps have heard or have not heard of, from pencil and paper. But we weren't consulted when the universe was created. And this idea that aspects of reality as we see it depend on a solution of the equations rather than on the fundamental equations may well be the way the universe is.
L'Organizzazione Europea per la Ricerca Nucleare, comunemente nota come CERN, è il più grande laboratorio di fisica delle particelle al mondo. Viene istituito a Ginevra nel 1954, allo scopo di creare un centro europeo in grado di eguagliare l'eccellenza dei laboratori statunitensi. Gli esperimenti condotti negli anni 50 e 60 all'interno degli acceleratori del CERN spalancano le porte della fisica a nuove prospettive. Gli scienziati osservano le collisioni tra fasci di particelle ad alta energia e scoprono l'esistenza di particelle elementari fino ad allora sconosciute. Queste scoperte danno il via agli studi sulle loro proprietà e interazioni. Dai tempi della sua fondazione, il CERN è stato dotato di acceleratori sempre più sofisticati, che oggi compongono una catena di strumenti in grado di portare un fascio di particelle a energie sempre più elevate. L'ultimo di questi è il Large Hadron Collider, entrato in funzione nel settembre del 2008. Si tratta del più grande e potente acceleratore di particelle mai realizzato. 27 km di tunnel sotterraneo ospitano un macchinario progettato con una precisione straordinaria, capace di accelerare protoni e ioni pesanti fino a una velocità molto vicina a quella della luce. Da questo sofisticato strumento, i ricercatori si aspettano di ottenere una risposta ai quesiti fondamentali della fisica contemporanea. Da quale aspetto avesse l'universo nei primi istanti della sua formazione, a quale sia l'origine della massa, all'esistenza di particelle supersimmetriche. I teorici delle stringhe oggi guardano a queste eccezionali tecnologie sperando che siano in grado di verificare le loro previsioni e che consentano di giungere un giorno a una comprensione più profonda degli affascinanti misteri della natura.
Looking ahead, one of the most important questions for fundamental physics is what is going to come out of the new accelerator, the Large Hadron Collider at the European Laboratory CERN near Geneva, and we're all very excited about what they might discover. One of the big questions is whether the LHC will discover supersymmetry. Discovering supersymmetry would mean finding new elementary particles, for example, a supersymmetric partner of the electron that would have the same electric charge as the electron, but would lack its magnetic properties. This would be a kind of modern version of what happened in the 1930s, when it was found that the electron had a twin with opposite electric charge. And in the 20s, when it was found that the electron actually had different spin states. So maybe the LHC, if we're lucky, will find that the electron also has a spinless cousin. And if it does, that'll put our understanding of nature on a completely new level. And speaking personally, I'd be delighted because in my career, maybe half of my papers have involved supersymmetry in one way or another. Supersymmetry and string theory have grown up together. Supersymmetry is an important facet of string theory, and there's at least a hope that the LHC will prove that it's correct. Speaking personally, I think that string theory probably is on the right track toward giving us a much deeper understanding of nature. And part of the reason I think so is that it seems to contain so many secrets about the mathematical and physical world, even in areas that string theorists didn't anticipate applying string theory to at all. In many areas of physics, the problem is that the equations are known, but they're too hard to solve. is really the usual problem of physics, except in areas of fundamental physics where you're trying to discover new equations of nature. An example is in heavy ion collisions. A heavy ion is the nucleus of an atom, such as a lead atom or a uranium atom. Physicists at the Brookhaven Laboratory in New York, and in the next few years also at the CERN Laboratory in Europe, collide together heavy ions, observe the collisions that come out, which are very complicated with thousands of particles coming out. And although the equations that are supposed to describe it are known, they're hopelessly hard to solve. String theory, however, led to an amazingly new technique for solving these equations, where these equations, even though they don't involve gravity at all, they involve ordinary elementary particle forces, are studied by comparing the real world in a situation where gravity is unimportant to a different description where gravity would be important, and modeling the droplet produced in a heavy ion collision by an evaporating black hole. So this is a striking success where string theory knows about equations encountered by physicists seemingly in other areas and gives remarkable insights which have caused string theory to be an important tool in explorations of heavy ion physics. And other things have happened in other areas, such as fundamental investigations of quantum phase transitions, which are important in studying states of condensed matter. In a way, I think the most significant criticism of string theory by other physicists may be that it's too ambitious, too big a step beyond what we know, and too hard to get the experimental clues that would be necessary to work it out correctly. Critics who take that point of view may even be partly correct, for all I know. Maybe we will always be in the situation of having an extremely rich theory that gives us tantalizing hints of something we don't fully understand. A widespread view among my colleagues, I think, would be agnosticism. Many colleagues would acknowledge that interesting and significant ideas have come out of string theory, but at the same time, since the reasons to believe that string theory might be on the right track are largely circumstantial, they would remain agnostic about whether string theorists are simply clever people who have come up with significant ideas about this and that, or are on the right track to a better theory of nature. Personally, I think that the circumstantial indications are convincing. What convinces me most is that the theory hangs together too miraculously to be an accident. It's generated too many good ideas about different areas of geometry and physics to be coincidental. It forces quantum gravity upon us, while standard quantum theories make it impossible to include gravity. And it qualitatively gives us, in an astonishingly effortless way, a good rough draft of the world of elementary particles.